with me this morning Alex Lee. He is electrical engineer and computer scientist with the Geospatial Research Laboratory, otherwise known as GRL, and we're talking about navigating the future, ERDC's digital buoy system. Good morning, Alex.
Yes, good morning. Thank you very much for having me on your program.
Well, thank you. And I'm so glad it worked out that you could talk about the digital buoy system this morning. But first of all, let's start out with talking about you. Can you tell me about yourself and your background?
I came to U.S. as a refugee from Vietnam. I then lived and went to schools in Southern California. I graduated from a California State University with a degree in electrical engineering with emphasis in computer chip design and minor in computer science.
Okay.
And I also graduated from a post-bac program in pre-medical at George Mason University in Virginia. And I have had various graduate coursework in computer science and biomedical engineering. As a professional experience after college in California, I worked for private industries as software engineer.
Mm-hmm.
Then I moved to East Coast, working for U.S. Navy in weapon R&D as an electrical engineer. And finally, in the mid-90s, I worked for U.S. Army Corps engineer at Topographic Engineering Center before I became GRL. Mm-hmm. As a computer scientist.
Wow, you have a lot of history.
Yeah, but throughout all my years working for the U.S. government, I've been working with water one way or the other, either with water navigation, mm-hmm. Water production for drinking water, and water operation to support the U.S. military logistic operation. Yeah.
Okay.
And this digital buoy is as a result of many years working for the core inland waterway, INC, Inland Water Charting, Electronic Charting Program.
Okay. So with that being said, what is your role at ERDC?
Yes, ma'am. At GRL over the years, I have worked on different R&D and reimbursable projects supporting various civil work and military programs, designing electronics, sensors, communication system, robotic system, and software applications. Among the customers that I supported, on the civil work side are the core headquarters, the core districts, USGS, NOAA, the U.S. Coast Guard. On the military side are different ERDC labs, various Army and Marine organizations. And also I currently supporting the civil work marine navigation and the military land robotics vehicles.
That's quite a role. And so I am happy to tell you that you are our first guest from GRL. So can you tell us where GRL is located and what the lab does?
Oh, yes, ma'am. I'm not pretending to know everything about GRL because we have about between 75 and 100 of engineers, scientists, mm-hmm. Analysts, and other technicians. And I only focus on what I'm doing, but I can tell you that the laboratory is co-located with the Army Geospatial Center in U.S. Army Corps Engineers Humphreys Engineering Center next to Fort Belvoir in Northern Virginia. Mm-hmm. So we are about 15 miles south of Washington, D.C. At GRL, we conduct geospatial research and development of geospatial technologies that will help the Army missions to better understand, to characterize, and to measure the physical, such as terrain, social, such as cultural, and environmental, such as water and air conditions. Mm-hmm. The research areas, for example, include terrain analysis and reasoning, spectral analysis, photogrammetry, terrain visualization, survey and mapping, image analysis, etc., etc.
A lot of et ceteras.
Yeah, I'm sure there are much more than what I just said. But
Okay.
as far as my knowledge, I'm limited to those areas.
Gotcha. So, I mean, again, you're the first one from GRL. We've had other representatives from all the other labs. So I'm just tickled to have somebody from GRL this time. So we're here today to talk about ERDC's digital buoy technology. Can you tell us what it is and what kind of problems that it helps solve?
Yes. So in the simplest terms, the technology covers both a hardware system and a communication method for real-time tracking and monitoring the water navigation safety buoys, quote unquote, the critical landmarkers for waterborne vessels. So traditionally and currently, the current physical buoys are just passive objects. Mm-hmm. Once they place in the water, they will start dripping away. And how much they drip depend on the local water and wind conditions. And periodically, they must be manually relocated back to the right place to indicate a safe water depth for marine vessel traffic. Mm-hmm. This whole process will take time and effort and coordinated by the Corps, by surveying, dredging, and charting, by U.S. Coast Guard for buoy tendering and maintenance, and the public for error reporting, mm-hmm. right? So all three of these entities have to work together right now for the current system to work. In the meantime, by some government report, up to 60% or more of U.S. agriculture and energy transportation and export output depend on the inland waterway. Mm-hmm. So you can imagine how critical is the waterway for U.S. economy. And accidents do happen annually in the waterway.
Right.
And a lot of those accidents are the type of grounding, ship grounding, the boat are colliding with the bridges. They traveling on the wrong side of the river, wrong channel, all kind of problems. So you can imagine, having a critical landmarkers are very, very essential.
I just don't think people realize just how important buoys are.
That's right. Yeah. Just imagine on the road when you drive, all the landslide disappear.
Right. That's a great analogy to look at. I mean, it's just like being on the road. Exactly.
Yeah. Yeah. They drip. They do drip, especially during low water, high water, flood, drain, all kind of weather event, either man-made or natural events. These buoys will drift away, and suddenly you have new landmarkers, and you can imagine, what would happen,
right?
If you get out of these set water depth,
right?
Yeah.
Well, with this buoy, though, I'm really curious about it. It must have many parts. What are the main parts that make it so smart and useful?
Yeah. So this technology would make the buoy smart by serving both a navigation and data communication functions for marine traffic and buoys management. The hardware system is very low power. It can run on a set of small batteries for months or years.
Really?
Yep. And the communication network itself is self-healing. Mm-hmm. So hence, the whole thing is low maintenance, right? You don't want to send people out there, all the time just to replace the battery, just to make sure they are communicating, make sure the network are forming, all that. You don't want to do that.
Right.
So you have to design and develop a system so that you can minimize all that maintenance. So the system can fix itself. That's what I mean. And it has a very long range. Right now, with this prototype, so between node and the right antenna with the right physical experiment, we can set it up and control the buoys, the physical location of buoy, and we can control the antenna so that it won't sway more than 15 degrees to the left or 15 degrees to the right. So then we can achieve up to or more than 1 kilometer between nodes, which is unheard of right now.
That's crazy.
Yeah, because imagine you have a Wi-Fi system at home.
Right.
It's only as good as maximum between 50 to 100 feet.
Right.
And it consumes so much power. You pump so much power through your Wi-Fi just to get that far, that long. And now with this system, really low power, run on set battery, and it can get up to or more than a kilometer between the nodes, which is very surprising to everybody right now. Yeah, and we are continuing improve on the range. The system is very smart. I wouldn't say it's radio software defined, but it's a software driven radio communication system. Mm-hmm. So we can change via the software the characteristic, the data reporting model, and timing and scheduling of each buoy. For example, we can put it to sleep when it doesn't have anything new to report, to say battery, right?
Right, sleep mode.
Yeah, when the weather report say, okay, this is going to be bad. There's high water coming down up from upstream down in 2 days or 1 day. Then we can over the air from an ERDC headquarters or somewhere reprogram it and reprogram the buoy on the Mississippi 1,000 miles away.
Right.
And we'll tell it to speed it up. Say, okay, from Monday at 10 o'clock to Tuesday at 5 p.m., speed it up. Pump out more report. Okay. Continuously. So that's another smartness of the system that we can do. You were asking about the parts of each buoy node. So each node essentially is a very, very small, very energy efficient computer with a radio transmitter and other sensors such as GPS, of course, to report the location. The current prototype has an accelerometer so that we can simulate or we can report an impact to the buoy, because the Coast Guard and other people in the Corps District telling us that people, the boat, the barge, the vessel are hitting the physical buoy all the time,
right?
Especially at night. And when they did that, bad thing would happen, because each buoy can have 1,000 pounds of the anchor or the buoy itself. It can damage a bow, it can damage spar, it can sink the buoys and all things like that. So right now we have accelerometers so that we can measure the G-force.
Is it lit up?
So when the buoy, no.
Okay.
They don't lit up. So at night you have to eyeball it, right?
Right.
Yeah. So with this digital buoy system, we have accelerometers so we can measure the G-force. So when something hit it, it can report that something hit it.
Right.
And then we can guess what would happen. And this prototype have a temperature sensor, so we can tell the environment, the air temperature. right now. So if something gone wrong, we can approximate how hot it is and, what kind of weather it is. And also it had a little light sensor.
Okay.
Just to simulate bad weather, right?
Right.
So the light will read the ambient light. So if it's a cloudy, stormy day, we can read that light level and we can tell, oh, it's really bad weather, and that's why the data look like this and look like that.
Okay.
So the sky's the limit on the number of sensors that we can put on the buoy that connect to the buoy computer.
Well, and as technology enhances, there's no telling how this system can be enhanced. So.
Yes, ma'am. That's right. Absolutely. And also the prototype right now for this current generation that we design, I'm using an ARM Cortex M CPU. It's been used in a lot of mobile device, not on your latest cell phone, of course.
Right.
But this CPU is optimized for very low cost and low energy, and it's a proven technology. We're not using anything exotic out there to keep the price low.
Right.
But we give it the new software algorithms. We reprogram it so it can keep track of locations of itself and its neighbor, and the radio signal quality of itself and its neighbors. And then it will schedule the data reporting of itself and its neighbor depend on various environmental and operational factors, right? Just like I just mentioned before, we can tell it to speed up, slow down, go to sleep, wake up over the air.
Right.
Yeah.
So buoys are so important for navigation, and I'm sure there are some challenges or limitations of the current methods of monitoring and tracking buoys on inland waterways. Can you tell us about some of those challenges that led to the need for this new technology?
Yeah. But first, let me give you a little background how we got involved with the buoys.
Okay.
Just to show you the point that we're not picking thing off the air and tell you about it. So back in early 2000s, we helped the U.S. Coast Guard to develop a system, a software system and database system to let the Coast Guard fleet of cutter, buoy tendering cutter, to communicate, to upload their buoy data. Every time that they go out there and service a buoy, pick up a buoy, repair it, and put it back in the right place. So they get the data point. Traditionally, they have to go back to the port if they don't have internet out there in the water. They have to go back to the port, and sometimes they have to manually enter into the computer system and send it via CD to us, because we are Army Corps engineer. Our mission is to get those buoy data and make a charts or map of it and send it out to the public for use. So the old system, they would take days, maybe a week or more, to update the buoy data to us. So back in the early 2000s, we developed a computerized and database server software to let all the ships, about 25 ships, to continue and update in real time to our server here in GIL. And then we can cut down the number of days in between and send it out to public. And then we transition the system to the Coast Guard so they can maintain it later on, a few years later, to update it. But it's still a manual system. They still have to go out there to be physically and visually nearby the buoys and relocate it back.
Right.
Or sometimes they have to depend on the public to spot our place buoy and tell us, so they can send the ship out there and put it back. So you can imagine, as far as we know, there's no method or system right now to monitor and track those buoys in real time. But on the new system, we would like, given all the advantages of low power, robust network, and low maintenance that I just talked about, we would like to do a longer term experiment on this system. We like to do in a wider range of seasonal weather and water condition. We would like to do a wider range of temperature from the heat to summer to the middle of the winter.
Right.
We would like to do the experiment with object and obstruction of radial path, so we can develop a better survivability and ruggedness of the system. So we still have some work to do. Yeah.
Always, you always want to improve what you got. So that's great.
Yeah.
So,
yes, ma'am.
But we've already touched on this, with the Coast Guard believing, the U.S. Coast Guard thinking that this is a game changer, and that's quite a compliment. Is there any more that you'd like to add about that technology that makes it so different and innovative?
So the reason you quote that, because we reported that right before pandemic, we have a program design review, and there are some Coast Guard local Coast Guard officer in the meeting, and after hearing us reporting about the system, he said, "Oh, this could be a game changer because of these things." Because earlier in 2010s, I get on one of the Coast Guard cutter during their buoy tendering experiment, and I set up these system experimenting with Wi-Fi, with cell phone, with AIS, just to show the Coast Guard that we can get the data from the physical buoy back to our server in GRL, do a geospatial processing it, and send the data back out on a map on the boat in real time within minutes, less than 5 minutes. So the experiment was great.
That's mind-blowing.
It was successful. Yeah, it was successful. However, it's not technical or economical feasible because the signal so range limited. The technology is too expensive, too power consuming. So it's nice to see the proof of concept, but there's no possible way that we can improve. We can build a system to do several miles at a time.
Right.
So now when we show them this, and the experiment that we did was on a 10-mile stretch of the Ohio River around Louisville district, and they say, wow. So that we can provide a real-time situation awareness, and hence the management of the system in real time.
Right.
And also we talk about this system, when it's in place, it can be a data backbone to support many, many potential applications. We can use a digital buoy to do the identification and monitoring of marine traffic, right? So the primary application to monitoring of the buoys, now we can in turn to use it to monitor the vessel, the traffic, passively, right? Because I wouldn't go in depth into why some of the vessel they turn up the system, identification system, they turn up or whatever it is, but we can silently and quietly monitor those traffic, and we can use the system to help marine navigation in GPS denied environment. So let's say for some reason somebody jam and spoof the GPS signal, or on that area, there's no good GPS signal because of trees or plants or anything. Now we can use the buoy system that we can do navigation without GPS. And also during experiment, we transmit text, SMS messages using the communication of the buoys. So we could implement a low bandwidth data communication for waterway and an alternate data communication, right? For some reason, some event happened, natural or man-made.
Right.
All the cell phone went down. And so suddenly you can turn on this digital buoy and you can talk to each other from the boat, or for someone out there in the Mississippi, you can send a text message to someone in Washington, D.C.
Using that system.
Digital buoy.
Wow.
Yeah. Another application is that we can send alert, microcharts, and maps to local mariners, right? Right now, if there's something happen at River Mouth 100 on Mississippi, and right now there's no way that we can let the local within a few miles around that buoy know, oh, there's a spill or something happened, that you need to take a detour, or you need to stop, you need to pull over somewhere and wait, right?
Right.
So now with this digital buoy, we can, from a emergency management office, headquarters somewhere, we can send this alert or update to reroute, detour to the local traffic at 1,000 miles away.
Wow, that's a wow moment. That's so useful.
And on land, there's nobody doing on land too, because right now you have to rely on a Google map, right?
Right.
And then you can see the traffic, either red or green or blue or yellow.
Right.
But it's all depend on your phone or the user phone to show the speed of that phone. So they will guess how slow that area, and then they will tell you. So what if we can put a note right out there on the highway and byway, and we can send these emergency services to the local area, and then when you're near it, and you see it right away. You don't depend on everybody reporting it. Yeah. So that's another use of the digital buoy that can reach over to land navigation also.
Well, one thing can expand to other things. So that's so great about research. That's what happens. That's awesome.
Yeah, and another one is very important that I've been talking to those hydrologists modeling from CHL and NOAA and GHS, and they say, hey, if this system in place, we can use it. We can do marine weather, environmental, hydrodynamics research of the whole column of water from the surface to the bottom. You can hang sensors on it, and then these researchers, the scientists, can do their own research and study using this digital buoy system.
Well, my husband, he works for CHL, and I was telling him about this show and who I was speaking with, and he definitely wants to listen because he's always out on the water, taking samples and doing all that. So he was very intrigued about what we were going to be talking about.
Yes, ma'am. Yeah.
So this year we're celebrating how the labs came together 25 years ago to form one ERDC, one organization of experts across multiple disciplines. How do you collaborate with other labs or organizations that assist with the digital buoy technology?
Oh yes. They're critical for us. For example, with the core district, right? We need to work with the district because we want to the help, the local help with the infrastructures like the bridges, lock, and dams, because this digital buoy, they need to route the data to the land line, to the land network somewhere, right? It have to jump off this waterway communication system to go onto the internet. So it needs to talk to the bridges, signal the bridges and the lock and the dam, marinas. Mm-hmm. And then we also need to have water survey, right? The hydrographic survey from the district, because we need to know where's a good location to put this node, mm-hmm. To optimize it, to make sure we get the best range out and best line of sight for the radios. So we need, and then also, of course, we need to operate the boats and the ships, and we can get the help from the district to do that. Mm-hmm. We can possibly, again, you just mentioned CSL. We can collaborate with CSL and or USGS for hydrodynamic modeling researchers for the local water conditions. Mm-hmm. When we did the experiment, there's a lot of micro hydrodynamic movement of the water at the local area. It's way different from the water a few hundred meters up or downstream. Mm-hmm. So we need the knowledge and the data model from the labs, from other people to help us, so that we will hopefully avoid these vortex, or we want to put the buoy in the vortex, for example. And we need to work with Coast Guard, mm-hmm. for buoys node deploying and placement, and for safety regulation and all of that. And also we need to work with industry, because we want to do it hundreds of miles and so many geographically separated river, right?
Right.
We cannot do it all by ourselves. We don't have enough manpower or time to do that. So we need to work with the industry for installation, for maintenance, servicing the system, et cetera, and et cetera. Yes. So we need to work with a lot of people.
As they say, together, everyone achieves more, right? I mean, that's part of team.
Absolutely.
Yes. So again, we'd already covered how the buoys can relate real-time messages to boats and ships, which is so super cool, about the water conditions and the location. So is there anything else you want to add to that conversation?
Yeah. So as we mentioned before, we can put different sensors on the buoy, such as GPS, light temperature, air, and water flow meters. So it can report a lot of water conditions. And in my earlier project, I designed different water sensor, water physical quality of the water. So we can put those water, and there are a lot of companies out there now that over the years that we talked to, they say, yeah, we provide these water monitoring for the state, for the local reservoir and all that. So if we have a digital buoy node nearby, we can enable our system to report to it and transmit the data back to where we want. So, yeah, we can do that. And so now, once the buoy are talking and transmitting data, so each boat or ship or vessel would either have a node on board, mm-hmm. in order to of course, we have to allow them. We have to give them permission, right? And they can get the data directly from the buoy, or the type of the sensor that it reported data that are relevant to that boat, or they can get a permission to connect to our cloud server. So because each buoy will also report the data back to the central server on the cloud, and so the boat can connect to our cloud server or internet and pull that data out. So everybody get connected and everybody can share data or get data. Yeah.
That's great. So how is precise waterway mapping and charting made possible by the digital buoy system? And does the system also communicate with the other buoys, and where's the data stored?
Yeah, yes, ma'am. So right now, let's talk about the accuracy of the buoy itself. So right now, in this experiment, we're using a GPS system that can have between 1 to 5 meter accuracy. And on the waterway, that's a very good, because a lot of systems out there would give you between 10 to 100 meter accuracy. Mm-hmm. So we're accurate. We're reporting the precise location of the buoys itself, right? Mm-hmm. And I was mentioning about using this system to navigate with our GPS. So now with a sensor to measure the signal accuracy, signal quality, and signal strength, so we can triangulate between, let's say, 3 or 4 buoys, and then we can figure out the location of the boat or the vessel. And so with each buoy have 1 to 5 meter accuracy. So in turn, by extrapolated, so the vessel can have the triangulated result within from 1 to 5 meters, just by talking to the buoys, right? And also, that accuracy also depends on the number of GPS that the buoys can see on the sky and the view, and unobstructed view to give you the best accuracy. But if it has a lot of obstruction or the sky view, the accuracy gets a little bit larger. So in turn, they will affect the boat. Right now, there's no other way for the vessel to navigate without with any other system besides the onboard GPS.
Right.
They either use the onboard GPS and depend on accuracy of their GPS, or they have to eyeball or visually looking out a window and navigate visually. Right now, you were asking about, so how do they communicate? So right now, each buoy will talk to its neighbor, mm-hmm. and its neighbor will relay the data up the chain until there's a terminal node somewhere, and it will jump out. So that's what makes this system low cost, robust, because it's a form of peer-to-peer networking. So you don't need a cell tower, you don't need some infrastructure, you don't need to buy land to build a tower, right? Because each buoy itself will be its own relayer. And in theory, the system can scale indefinitely.
Well, I go with what the U.S. Coast Guard said. I believe it's a game changer.
Okay. And right now, all the data is stored on local memory of each node. So it has a small set of RAM locally. So it will store its initial location, and then it will continually update and store all the historical location after that. And then in the software algorithm, it will continue to measure how far it's drifting away from this initial location. And if that's beyond a safety windows, then it will send out the alarm alert. Right?
Okay.
Throughout the system and say, hey, look at me, I'm way off. I need to be relocated back.
Right.
Or if the Coast Guard, the Corps, or the local operator, they don't have time to service it, and then we can say, hey, all right, we can put a synthetic buoy, synthetic symbol on back to the right place. So make it blue, okay?
Right.
And the physical buoy, we can make it red to tell people, okay, so this physical buoy right now is way out of place. Don't rely on it. Need to look at this blue synthetic symbol that we just put out, for example. So that's one way that it can communicate, and then it can communicate with us, and then we can do something about it.
So as we wrap up today, it's been a pleasure learning about the digital buoy system. And what would you like listeners to learn from this valuable conversation?
Oh, gosh. Yes, ma'am.
It's hard to sum that
up. I'm not sure I'm the authority on this, but I like to say this is an effort resulting from a multi-year, long-term engineering study and field experimentations. Mm-hmm. Many years ago, we did it once to show the proof concept. It wasn't possible to do it. We put it aside. We work on some other engineering problem, And while doing so, we gain more technical knowledge. And then we also need, as a researcher, we need to keep up. We need to keep up with the technologies, with the knowledge, and periodically we need to revisit the problem if it's still there. Mm-hmm. So that's. And then the last point I want to say has 3 words: perseverance, persistence, and teamwork.
Awesome. Those are great 3 words to sign off with. Well, Alex, thank you so much for participating in the show today. It's been a pleasure.